Carbohydrates are built upon monosaccharides. Monosaccharides are one single ring unit made up of carbon, hydrogen, and oxygen atoms. It is a ring primarily of carbon atoms with one oxygen link. Glucose is also called blood sugar. It is the form of carbohydrates in our blood. Mono means one. And we find that these monosaccharides, or simple sugars, we have different isomers. Remember isomer? It's the same formula, chemical formula, different structure. So one other very common monosaccharide is fructose, or fruit sugar. This is a 5-membered ring. Glucose has 6 members in its ring. You'll notice that we have this species coming off of the ring, an alcohol. Alrighty, now these are the basic building blocks of our other carbohydrates. Disaccharides. As you might expect, di means 2, and these are 2 joined monosaccharide units. These aren't that uncommon. Sucrose, that's table sugar. And lactose, that's found in milk. This is an interesting point too. Different sugars, different mono and disaccharides have different levels of sweetness. You think of all sugar being the same. No, these have different levels of sweetness. And in order to make sucrose, we're going to take a glucose unit and a fructose unit, put them together by this lovely little link right here of an oxygen, and we spit out water. You notice the chemical formulas. And again, see, the glucose and the fructose have exactly the same formula, different structure. Remember, he's 5-membered, he's 6-membered, and they make sucrose and water. Last but certainly not least are the polysaccharides. These are also called complex carbohydrates. Okay. All right. These can be huge. These are long chains of these monomers, these monosaccharides, right? You know, notice how this is 1 and 2. 1 plus 1 here equals 2. But for these, we can have chains of thousands, molar masses in the millions, highly branched too, like so. They're all over the place. We are going to look at 3 families: starches, glycogens, and cellulose. All right. Starch. It's important to remember that this is like a family. These are a family of chemicals. They all have the same kind of properties though. They're all linear, long linear, okay? They occur widely in plants, and they're used as energy storage by plants. Plants don't have fat in them. They use carbohydrates exclusively to store their energy. And when eaten, our body breaks these down into simple glucose units, which then are absorbed into our bloodstream and taken all over our bodies. You can feel it start in your saliva. The enzyme in your saliva initiate the process of breaking down the long polysaccharide chains into these glucose molecules. In fact, that if you chew a cracker, which has some starch in it, it becomes sweet. That is, it's breaking down into mono and disaccharides, which is kind of cool. And then your body does more of it in your stomach, more in your gut, in your intestines. And it is the glucose that your body uses. Okay. Glycogen, probably something you haven't heard of. Now, starch, yes, you've probably heard of, but not glycogen. Glycogen, though, is more important to your body because this is animal starch because it's the major source of energy in animal tissue. For us, it's mostly in our muscles and it's in our liver for quick energy supply. So many things happen in your liver, but your muscles, you can probably understand, need energy quickly. It's synthesized from the body from glucose units in the blood sugar. It's highly branched. That means not linear. This changes its properties, its chemical reactions, just like we saw with, let's see, what was it? Isooctane versus octane. One has an octane rating of a negative octane rating, which means it really stinks for knocking and premature ignition, and isooctane, which is the standard that has an octane number of 100. Okay, and the last but not least is cellulose. This is very much like starch, unbranched long chains of glucose isomers. Now here's the rub. It's the structural unit of plants. It's the cell walls of plants. Not found in animals. And it's got the same fuel value as starch, or all carbs. But it is indigestible by us. We lack the necessary enzyme to break the linkages between the glucose units. Now, who can break them? Well, ruminants can, like deer and cows do. And so they can obtain the energy from these cellulose units, and they break it down into glucose and its isomers, okay? Glucose, which again is the same routine, broken down then into your body, into your bloodstream as glucose. But it's interesting. It is just the linkage between the glucose units. Okay, so this is why we cannot eat grass or our textbook for fuel. You are not in a position to be able to just sit and gnaw on your notes as you take a test. The starch we can digest, and that's fine. But the cellulose passes through our system without undergoing significant chemical change. We call this roughage. Is that bad? No, not necessarily. These guys can break it down, right? In fact, they make methane as a product, which is an important greenhouse gas, especially when you go to someplace like Australia, where they have, you might know, all these sheep, and they're putting out, that's their biggest source of greenhouse gases, not cars. And how do you control the greenhouse gas coming from, well, let's be delicate, from the digestive tract of a sheep? But we do need fiber. This is the cellulose that's in the foods, especially vegetables and whole grains. Right? That's why you want to eat whole grains, because along with the polysaccharide starch, you get a lot of other stuff that your body needs, like nutrients, B vitamins, and fiber. Fiber has not been very, well, people didn't talk about it much before the 60s, but it is very important to our bodies. It can be soluble or insoluble in water. It binds with fatty substances like nasty cholesterol and then takes them out of your system. The insoluble stuff is all cellulose. This is called roughage. And just because your body doesn't glean any nutrients from it does not mean it's not important. It softens and adds bulk to your solid waste and moves it along. So you don't want pounds of fat and protein sitting in your stomach or in your intestines. Right? It adds to fullness. It helps release and slow down the release and absorption of glucose, so you don't have a wide fluctuation of blood sugar. And of course, this is most important to diabetics. And I don't know about you, but I can feel that when I eat a donut for breakfast, and I feel pretty crummy by the middle of the morning. Usually foods containing fiber, I just said that, are packed with other nutrients. Oatmeal, fruits, whole grain, seeds, cruciferous, that means crunchy, like broccoli, peas, and beans are all very good sources for this material. Another problem we have with digestion has again to do with this linkage. Lactose intolerance. Believe it or not, 80% of the world is lactose intolerant. And that's why you don't see a lot of cheese, milk, or ice cream in Asian or African diets. Lactose intolerance is another example of us lacking an enzyme, in this case lactase, the ACE. It means it's an enzyme. And this catalyzes the breaking of the lactose into its component monosaccharides. The result is that this stuff ferments in our intestine. Oh my gosh! If you are lactose intolerant, and you've ever had drunk milk, and you get that horrible pain in your intestines, oh, the cramping and the gas and the diarrhea. But it's all because we have these rings, right? And if you'll remember, let me do one with oh yeah, let's do one with. Okay. All right. So this is coming down here, and let's do a linkage between two. We also have this CH3O coming off, but let's not worry too much about that. So we have the monosaccharide unit, another monosaccharide, and we can break this linkage. This is, if this was 5, it would be sucrose. Okay. So this is cool. We can break this into fructose and glucose. All right, starting off with the two-membered sucrose. All right. But if we have a different kind of linkage, like this, isn't that amazing? This is another mono unit. We put oxygen up there. And they differ by, where this guy comes off here, the alcohol there. All right. We can't break. We can't break this linkage. I think that's amazing. Oh boy. And so what happens is it's left to break it down in our intestines with all sorts of different kinds of methodology we don't want to think about.